So in those previous examples, what we did is we ignored sodium and we ignored chloride, and I didn't really talk about like why we ignored them, okay? So the simple rule is this: is the hydrolysis that or protonation reactions that produce strong acids or bases do not occur. Okay, so for example, to go back to the sodium acetate. So we already figured out that acetate makes a acetate ion makes the weak acid acetic acid. So that's a reaction that'll occur. So that, in other words, AC minus plus H2O makes HAC plus OH minus. This will occur because this is a weak acid and it doesn't like being ionized. Okay, it likes having its proton on. Okay, so if I take sodium and I do the same kind of reaction, now you have to remember sodium will react with water as well, or can react with water. And if it does that, what it does is it pulls the OH off instead of the H, right? So if you think about acetate, it pulled the H off because it's the base. Sodium will pull the OH off, and you'll get sodium hydroxide like this, plus H plus. This can't happen because sodium hydroxide likes being without its proton, right? And so it likes to dissociate and be as sodium and water. Sodium hydroxide is a strong base. When you think about this equilibrium, it's really all in this direction. And so we'll do the same thing for ammonium chloride. Cl minus, well, do ammonium first. NH4 plus H2O makes NH3 plus H3O plus. So this is not a strong base. Okay, so this is this is an acid. It produces a weak base. And as a result, right, it can't completely remove the protons from the hydronium it created. And so this is actually an equilibrium reaction. It goes back and forth. Okay, so then we'll look at chloride. And chloride, if you put it with water, will cause hydrolysis of the water and make OH minus. But this is a strong acid. And the same rule applies. It doesn't like being that way. It prefers to be to the left and as chloride ion, because it's a strong acid, likes to fully dissociate. So that equilibrium is lying far to the left. So chloride can't affect the pH either. So if I take ammonium chloride and I put it in solution, the ammonium will make it acidic, but the chloride can't make it basic. So overall, ammonium chloride makes the ammonium chloride makes the pH go down, and sodium acetate, because the sodium doesn't want to be forming sodium hydroxide, but the acetate likes to pick up the proton and make hydroxide, then the pH will go up. Okay, so we can summarize it like this. If the cation comes from a weak base, right? If the cation comes from a weak base, it will make the solution acidic. More acidic, I should say. On the other hand, if you have a cation that comes from a strong base, then what happens is there's no effect. Now you have to remember the cation has a positive charge, so if that makes it easier for you, protons have positive charge. If the cation has a positive charge, it can make the solution acidic by hydrolysis. Now, if the anion comes from a weak acid, it can make the solution basic. And if it comes from a strong acid, it has no effect. Now, there's 4 different categories that this can be broken down to, because you realize you have a weak base, right? And that could be paired with a strong acid. So this would be the salt of a weak base and a strong acid. That's the way it's said. Okay, that would make the solution more acidic because the part of the salt that comes from the strong acid has no effect. Now this can get really confusing, but it turns out there's a simple way of organizing all the information like this. So what I did is I created a table and I put cations at the top and anions on the left. And the cations either come from a strong base or a weak base. Now, very quickly, you can eliminate any changes caused by strong bases or strong acid. Oh, the highlighter doesn't like that. Okay, I'll go like that. Now, those have no effect on the solution, but the weak ones do. So what you're going to be looking at is you're going to be looking at these guys to see what effects they have, okay? So what we'll do is we'll talk about then what the possible solution outcomes if your salt is composed of one from category of the anions and one from the category of the cations. Okay, so if it's a strong base and a strong acid, so now we're here in the categories here, right? If the salt is a salt of a strong acid and a strong base. So example, sodium chloride is a very common example. Comes from, right, NaOH, and HCl. Right? That has no effect. Neither one can change the pH, so the solution pH remains unchanged. In pure water, so let's talk about the cation coming from a weak base, so that would be ammonium chloride, for example. Okay, so that's a weak based cation, strong acid-based anion. This would come from, for example, ammonia and HCl. It's the product of that reaction. Well, the strong acid anion doesn't have an effect on the pH, but the ammonium ion, which comes from the weak base, can, and so the solution will become acidic. And if you're or more acidic. So if you're adding ammonium chloride will produce hydronium more than it will hydroxide. And as a result, you end up getting a more acidic solution. Now, the opposite is true if the cation comes from a strong base and the anion comes from a weak acid. That's down in here. An example could be something like potassium fluoride, just to pick something different. This is the salt that is produced by KOH and HF, like this. So if that's the case, right, then what happens is the KOH can't have any effect. The cation cannot have any effect on the pH because it comes from this strong base, KOH, and KOH won't form back in solution. And then the fluoride ion, right, wants to form the weak acid HF, and so what you end up getting is a solution that becomes more basic. So the pH will be greater than 7. It won't be neutral anymore if you start with pure water. So the solutions become more basic if you add a salt of a strong base and a weak acid, or become more acidic if you start with a salt of a weak base and a strong acid. Okay, so you always, when you're hearing these referred to in the text, they're always referring to the cation and then the anion. Now, the complicated or the more complicated one, and I know this can be really confusing, so I'm not trying to say this is necessarily easy, but it's nice to have a chart to recognize there are only 4 possibilities. Actually, it turns out there's 5, but we'll talk about the 4th and 5th possibilities now. What if it comes from a weak base and a weak acid reaction? So, for example, you have, get back to the pointer, let's say ammonium cyanide, NH4, CN, and we'll tackle this problem, one just like this or this one exactly, later in these slide series to show how you calculate it. But I just want to show you very quickly how you think about this. So this comes from, though, ammonia, which is weak, reacting with HCN, like that. That's the acid-base reaction. And ammonium cyanide would be the salt. How do you know what the pH is going to be more acidic or more basic? And for these calculations, you're not going to be asked, for this particular type, when you have weak base, weak acid salts, you're not going to be asked to calculate the pH, but you'll have to guess like whether or not it'll go higher or lower, okay? And the way you do that is you say, well, what happens when I do this? I have NH4, right, plus water, and you're just going to do the acid ionization reaction for ammonium. You'll get NH3 plus H3O plus, and this is going to be a Ka reaction, but you're going to have to get that from Kb. And then cyanide, well, it's going to hydrolyze water, so I have Cn minus, and I'm going to add water, right, and it's going to form HCN plus hydroxide, like this. And that's going to be a Kb reaction, but you're going to have to get that from a Ka. So both of these reactions are going on at the same time. They're different, though, than what we looked at before, because now they're not producing, where we have 2 equilibria, they're not producing the same. They're actually producing 2 ions that could react with each other. That is, the hydronium and the hydroxide could react with each other. And that's what makes the actual calculation, like of an exact number, more difficult for these. So what we do is this. We just want to know whether it's going to be more acidic or more basic. And the way you tell that is you just look at the size of the Ka and the Kb. And whichever one is bigger, that one's going to be producing either the more hydronium or the more hydroxide. So if Ka is bigger, you'll have more hydronium and the solution will be acidic. If Kb is larger, then you'll have more hydroxide than hydronium and the solution will be basic. So here's the example I have from my slides and from my notes. It's for ammonium cyanate, so not ammonium cyanide. I remembered wrong. But same principle applies. Cyanate is the conjugate base of a weak acid. Right? So I'm looking at this as a formula like a CNO minus. And I don't know what that is necessarily, but HCNO must be the acid because the negative, right, implies that it lost a proton. And then the NH4 plus, that's the conjugate acid of a weak base. And so then I have these 2 reactions to consider. And the question is ammonium ion a stronger acid than cyanate is a base? And so I'm just going to step you through this. I sort of did all the work. We're going to figure out which is stronger, acid or base, and whichever one's stronger determines which reaction will dominate in the equilibrium and whether the solution will be more acidic or more basic. So I went and looked up the Kb for ammonia, and then I went up and looked up the Ka for cyanic acid, and then I calculated for the ammonia the Ka value, and that's just Kw divided by Kb. So now I have the Ka for this reaction. And then I did the same thing for cyanic acid and found the cyanate ion, right? And then calculated its Kb, and then I got Kb is equal to 5.0 times 10 to the minus 11. And so which one's bigger, right? Kb for ammonia is greater, sorry, Ka for ammonium is greater than the Kb for cyanate. Not by a lot, but an order of magnitude, right? So it's quite a bit in some ways. And that means the solution will be acidic because the acidic reaction dominates. So the next thing I want to look at is this general idea of the rankings of acids and bases and their conjugates. Okay, so what I've done is I took a whole bunch of acids and I listed them on the left, and a whole bunch of acid and a whole bunch of conjugate bases or bases and listed them on the right. And this is the idea: the stronger the acid, the weaker its conjugate base. So, for example, perchloric acid is one of the strongest acids that we have, and so that means its conjugate base is the weakest. In essence, when you're looking at these reactions, just summarizing as H3O plus H3O plus like this, right? The reaction is going in this direction. If the base and the acid could both be strong, then it wouldn't make sense, because then if the base was strong, it would be picking up the proton and going back to the acid. So the idea is the strong acids conjugate bases are very weak, and for weak bases, weak acids, the conjugate bases are very strong. And you can kind of get that idea just from this. Kb is equal to Kw over Ka. The bigger Ka is, the smaller Kb will be. And vice versa. For bases, we can have the same kind of trend. That is, the strongest bases produce the weakest conjugate acid, and the weakest bases produces the strongest conjugate acids. Okay. So that's just this is a listing of acids from a very old textbook, but I thought it was real useful to think in terms of strongest and weakest.